In this video, we are going to remember which conservation laws we are going to solve. We are going to address a couple of example problems that are already familiar to you. The conservation laws that we have listed so far were the conservation of mass. And of course, in addition to the overall conservation law, we have species mass balance also. Then we have conservation of energy, and we have conservation of momentum to address. The conservation laws will be applied around the system of our interest, and we are going to ask several questions. First of all, we are going to ask whether our system is close to equilibrium in terms of thermal energy transfer and in terms of chemical conversions. And then we are going to ask the question of the rates of these events. So one quick example: if the system is thermally equilibrated, then we conclude that the temperature is neither a function of position, x is our position vector, nor a function of time. If our system is at chemical equilibrium, no net chemical conversion can take place. We're going to discuss this later in the semester, in the later videos. Let us start from a process where we have thermal equilibrium. In other words, the system temperature is independent of position and time. In other words, we maintain a constant temperature within the system boundaries. So we're going to look at the example. Of a constant temperature well-stirred reactor. The constant temperature condition relieves us in terms of problem complexity. Let us select our system as our well-stirred reactor. Where our hypothetical A goes to products reaction is taking place. We have FA in the units of moles per second enters the reactor, FA out moles per second leaves the reactor. This A goes to products reaction has a constitutive rate expression given by minus R sub A, that is equal to K times Ca. The power of the concentration is unity, indicating that the reaction is first order. And this minus sign in front of Ra indicates that A is depleted during the process. So we are going to write the species conservation equation or the mole balance. I'm going to divide the board to maintain the information here in order to refer back when needed. And let's continue from here. We are going to write a general conservation law. The general conservation law is of the following form: time, rate of change of the conserved quantity is equal to the rate with which the conserved quantity crosses the surface boundaries Let me use theta to indicate the conserved quantity. Theta enters through the surface boundaries and the rate with which theta leaves the surface boundaries. The rate with which theta leaves the surface boundaries. This is the general form of the conservation laws. And theta can be mass, temperature, or momentum, but not the moles, right? Because moles are not conserved quantities. Theta is either mass or energy or momentum. Theta is not the moles. Theta is not the temperature. Moles and temperatures are constitutive relationship demanded characterizing variables. We call mass, energy, and momentum as fundamental dependent variables. Fundamental dependent variables have their conservation laws associated with them, and we may have a derived dependent variables, fundamental dependent variables. I have to be precise here. Fundamental dependent variable we call a dependent variable fundamental dependent variable if we can write a conservation law for that fundamental dependent variable, if we need a derived variable to be able to easily solve this problem, then that dependent variable is the characterizing dependent variable. Now we can write the conservation law for mass, but mass balances are very difficult to solve in terms of reaction kinetics expressions. It is very difficult to incorporate the rate expression into the overall mass balance. And we can relate mass to moles, and we can write mole balances, which are easier to handle mathematically, and we can incorporate this constitutive relationship of rate expression in the mole balances and solve this problem with a more convenient mathematics. So if we take the mass and divide it by the molecular weight, we get the moles. All right, you get the moles. But the nature of the problem is that because of the reactions, moles can be generated and consumed. And now, when we write a mole balance, it is no longer a conservation equation, but it is a balance equation. So we still have the same concept, time rate of change of, but this is no longer a conserved quantity. So we are going to write the mole balance. Time, now I'm using the language of math. Time rate of change of number of moles of component A within the system boundary. And A is the number of moles of A within the system boundary, is equal to the rate with which moles enter through our system boundary. Our system boundary is this reactor. The rate at which A crosses the system boundary, it crosses the system boundary with this rate. Let's check the units. Na is moles, T is time. Let's use second in terms of units. FAN is mole per second. Minus the rate with which theta leaves the surface system boundaries, FA out. Again, this is mole per second. And now I have another term. The rate with which A is generated. And now I'm going to write RA times dV, and I will integrate over the volume. The reason that I have put this equation in such an integral differential equation is because I have been telling you about the temperature non-uniformities, the concentration non-uniformities, and even inhomogeneities in the flow domain. And as such, I anticipate a non-uniformity in the reaction rate, and by integrating throughout the reactor volume, I obtain an average reaction rate. And of course, the reaction rate has the units of moles per second per liter multiplied by liter. This whole equation has the units of moles per second, and we have an equation that is consistent in units and dimensions. Now this is the general mole balance for this reaction taking place in this reactor. We can take Ra out of the integral if the system is uniform. Uniform means that there are no change in concentration with respect to position. I'm going to solve this problem twice. First time, I'm going to invoke the steady state condition. So I'm going to solve this problem in two different ways. The first solution will be the steady state solution, where we are going to render dNA over dt to be equal to 0. In other words, there is no time change events in this reactor. And then in the second case, I will solve this problem for an unsteady state condition. Now let's first get the steady state solution. For the uniform systems, our rate expression enters as Ra times V. dNA over dt is equal to 0. That is going to be simplified as Fa in minus Fa out plus Ra times V. And before I rearrange this equation, I will convert the flow terms to terms in terms of concentrations of the species I and the volumetric flow rate of the stream. I will call it V0. So Fa in is going to be Ca in times V0. Fa out will be Ca out times V0. I will make another assumption here. I will say that for situations that we have volumetric flow rate that is constant, in other words, it is not changing with respect to time, this equation is going to simplify as V to be equal to Ca in minus Ca out divided by minus R sub A, and I'm going to carry V0 onto the side of this equation. Now this end has if you pay attention, this has the units of liters, units of volume. This has the units of volumetric flow rate, liters per second. As a result, this whole group has the units of time. We're going to label it as tau, and we will call it the space-time. Time it takes for the reactor contents to run through the space. And this equation is the design equation for a CSTR operating at steady state. Design equation of a CSTR operating at steady state. Okay. Given this, in a small frame that is left for me here, I will substitute RA and solve this equation. Tau is equal to CA in minus CA out divided by minus R sub A was given to us as K times CA. Now what is the CA? This CA is CA out. This is CA out because of the uniformity condition that inside this reactor concentration is equal everywhere, including at the exit of the reactor. I will rearrange. I'm going to obtain a new expression as tau K to be equal to CA in minus CA out divided by CA out. Okay. The unit of K is 1 over seconds. The unit of tau is seconds. And tau K is a dimensionless number, which we call the Damköhler number. We will learn more about this. Now this equation, in terms of Damköhler number, can be solved for the outlet concentration. CA out is CA in divided by 1 plus tau K. So, what does this equation tell us? This equation tells us that the outlet concentration of species A, the reactant, depends very strongly on the inlet concentration, on the reaction rate constant, and on the space-time. We can play with the inlet concentration by changing the concentration. We can play with the reaction rate constant by playing with the temperature. We can play with the space-time by either changing the volume of the reactor, which industrially, which is not very easy, but we can change the space-time by changing the flow rate that comes into this reactor, which is relatively easy, where we can do our engineering. In solving or deriving the design equation for a CSTR, you may have noticed that we have no dimensions, nothing related to position, nothing related to time. And as a result, these type of reactors are also called the zero-dimensional reactors. All right, now we are going to introduce the time dimension into the expression. In this problem, part B, unsteady state. Unsteady state reactor. We have dNA over dt term remaining. In this case, that due to some event, number of moles of A is changing within our system boundaries. Startups and shutdowns are very good examples of the unsteady state behavior. dNA over dt is equal to FA in minus FA out plus RA times V. Remember, our reactor was uniform and we took RA and V outside the integral. Now we are going to substitute again everything in its place. FA is equal to CA in times V0. FA out is CA out times V0, and RA is K times CA out times the reactor volume. Now what is Na? Na is a number of moles of A within the reactor. Na is equal to the reaction volume times Ca in the reactor. And Ca in the reactor so far is represented by Ca out. And as such, if we are going to take the total derivative of this, we're going to end up with two pieces of information. Ca out times dV over dt plus V times dCA out over dt. Of course, there are two reasons that an unsteady state condition can happen in a reactor. One is that you may have a volume change, and the second situation is that you may have a concentration change with respect to time. So we are going to solve this problem for a constant volume reactor. As a result, this term disappears. So we have V dC out over dt to be equal to Ca in minus Ca out, the common parentheses of V0 minus K times Ca out times V. We're going to rearrange to cancel V, make this 1 over tau. And then we are going to regroup this in terms of constants and variables. We have an ordinary differential equation. This is supposed to be CA out. CA in over tau minus 1 over tau plus K times CA out. This is a first order ordinary differential equation which requires a boundary condition. And the boundary condition is it has to come in terms of relating time to the concentration. So we have at time t is equal to 0, CA out is equal to 0. There was nothing in this reactor. Solution and its relation to the whole problem will come in the next video.